You've probably seen a curve cross the x-axis once, maybe twice, or maybe a few more times. But how about infinitely many times, or even more than that? To answer this question, or even be able to formulate it mathematically, we need to make use of real analysis, which is the rigorous study of numbers, functions, and how to do calculus with them. But for any student studying analysis, a necessary prerequisite is always multiple courses in calculus, and certainly a good sense of what numbers are like. It seems somewhat paradoxical that you're expected to have already studied and used calculus so extensively before taking a course that properly defines what calculus actually is. And to add to the irony, despite being regarded as one of the most challenging math classes, taking it will barely help you differentiate functions or compute ridiculous-looking integrals. So why is it that a course which seems to offer so little on the surface ends up in nearly every undergraduate maths curriculum? Well, this is because real analysis builds a strong foundation for most other areas of maths, as well as science and engineering. After all, a skyscraper cannot be built on a shaky foundation. In this video, we wish to give an introductory taste to this course through two examples involving the Cantor Set, as well as showing how it can shatter intuition. The word intuition will be thrown around a lot, but it's important to realize that intuition is just intuition and can be unreliable and misleading at times. I hope to display this idea well through this video and show that a rigorous framework that analysis provides is much needed. Finally, I should apologize that despite preaching rigor, some of the ideas I'm working with are slightly informal to make the arguments more approachable. With that in mind, let us jump to the first example. We'll start on a concept that we'll use for the rest of the video, which is cardinality, a way to assign a size to a set. We'll define what finite, countable, and uncountable sets are, and classify the size of some well-known sets. A set is a collection of objects, and they're denoted with these curly brackets. A subset of a set is a different set that takes some of the items from the original one, and is denoted with this symbol. Note that sum here could mean taking none of the items or all of them. If a set only has a finite amount of objects, obviously we can just count the number of elements in it and call that the size or cardinality of the set. Things get a lot trickier when we have an infinite set, like the set of natural numbers. If we try to count the elements in it, surely we'll be here forever. To continue, we first need to define what injective, surjective, and bijective maps are. The concept is crucial for the entire section, so make sure that you're familiar with it. The word map, or function, takes elements of one set to another. This could be taking shapes to numbers, or expressed by a formula like f of x equals 2x. Two different maps are shown here. If we look at the one on the left, different shapes go to different numbers. We call these injective maps, which takes different inputs to different outputs. The one on the right, however, has both the circle and triangle maps to one, so it is not injective. However, every number is being mapped to by at least one shape. We call these surjective maps, where every input is being mapped to. The left map is not surjective, as 3 is not mapped to by any shape. Finally, this new map, as you should verify, is both injective and surjective. We call this a bijective map, and I'll denote these with double arrows. There are a few ways to rephrase having a bijective map. We could say that there's a one-to-one correspondence between sets, or that the map has an inverse that is well defined. The last thing to bring up is that having a bijective map between two sets means that they have the same size, or cardinality. Here is a slightly tricky example. Take the set of regular polygons and natural numbers. The map taking the polygon to its number of sides minus 2 is a bijection, as you should verify. So here is a quick recap before we move on. Going back to infinite sets, a set S is countably infinite or countable if there's a bijective map from S to the natural numbers n. So by this definition, n itself is countable, as we can simply map each number to itself, which is clearly bijective. Since being countable means you can assign a number to each element, this means we can reference elements of the set by the numbers. So the set could be indexed as S1, S2, and so on, which will be very useful later. Finally, if S is neither finite nor countable, we say that S is uncountable. Intuitively, we can think of this as being too big to fit inside of n. Next, recall the definition for being countable. We can actually relax it to say that S is countable if there's an injective map to N, given that S is not finite. We still need different inputs to map to different outputs, but you no longer need to map to every single natural number. In order to prove this, we need to show that if we have an injective map from S to N, then we also have a bijective map from S to N. Let's start with our injective map, and consider the set of numbers being mapped to. If we now add a different map that takes the smallest number of it to 1, then the second smallest number to 2, and continue this forever, we can combine the two maps together and end up with a bijective map. And we're done with the proof. Armed with our knowledge of cardinality, let's try to identify the size of some well-known infinite sets. The integers is the set containing the natural numbers and their negative counterparts. Intuitively, this set has double the elements as the naturals, so surely its size is a higher class, right? Well, no, in fact, it is also countable. We have to craft a bijective map from Z to N, and this is how we go about this. We split the integers into the negative and non-negative halves, and take the non-negative integers to even numbers. So 0 goes to the first even number 2, 1 goes to the second even number 4, and so on. Then we take the negative integers to odd numbers. -1 goes to the first odd number 1, -2 goes to the second one, which is 3, and so on. It's clear that this is a bijective map, therefore Z is countable, and with this, we found an example that doubling an infinity gives you the same infinity. A key fact that we'll use here is that each natural number can be decomposed into a unique product of prime numbers. Therefore, a different product of primes must give different numbers. Let us only deal with the positive rational numbers. We note that each of them can be written in the most simplified form of P over Q, where P and Q are natural numbers. Now we define the map F that takes P over Q to 2 to the power of P times 3 to the power of Q. Here are some examples of applying F to rational numbers. We claim that F is an injective map from Q to N, so we need to show that different rationals are mapped to different numbers. In other words, if two rationals map to the same number, then they must be the same rational. Suppose that two rationals, P1 over Q1 and P2 over Q2, are mapped to the same number. Then 2 to the power of P1 times 3 to the power of Q1 is equal to 2 to the power of P2 times 3 to the power of Q2. But since these are product of prime numbers 2 and 3, they could only be the same if P1 is equal to P2 and Q1 is equal to Q2, which is saying that the two rationals are the same. So our map F is actually an injective map. So now we know that the positive rationals are countable. But you might be thinking, surely this is cheating. There are so many more rationals than natural numbers, yet we can somehow make an injective map with so much unused space in N. And this is a completely fair reaction, as the concept of infinity is known to defy seemingly obvious intuition, as you may continue to see later in the video. It's actually true that the set of all rationals, even with 0 and the negative ones, are still countable. As an exercise, try to prove this. Coming straight from the previous success, we might think that the reals are also countable. There's actually a solid piece of evidence for why that could be the case. The rationals are known as a dense set, so in any interval, no matter how small it is, there's a rational number inside. What this means is that the rationals are essentially everywhere in the real line. Which makes it even more shocking to know that the reals are actually uncountable. For the longest time, mathematicians thought that infinity is just infinity, and they are all the same size. But in 1891, German mathematician Georg Cantor showed that the reals are a bigger size than the naturals, with his famous Cantor diagonal argument. The argument focuses only on the closed interval 0-1. The closed interval AB refers to the set with all numbers between A and B, including A and B themselves. And in this video, an interval with 1 point does not count as an interval. With that in mind, we'll assume that each number in 0, 1 can be written out as a unique decimal expansion. Then our plan is to use proof by contradiction. First, suppose that 0, 1 is countable, then show that it reaches a contradiction, and hence cannot be true. Since 0, 1 is assumed to be countable, we may index it and write the set as A1, A2, and so on. This is saying that for any number between 0 and 1, it is one of the ANs, and we plan to show that there is always a number in 0, 1 that is different to all the ANs, to reach the contradiction. Now, laying out the AN's decimal expansion in a table like this, we highlight the numbers on the diagonal, and define a new number b as follows. We define the first digit after the decimal point of b to be 6, unless the same digit in A1 is also 6, in which case we bump it up to make it 7. For the second digit after the decimal point, we do the same thing. It will be 6 unless the second digit of A2 is the same, and in that case we'll make it a 7. This process keeps going, and in general, the nth digit of b is 6, unless the corresponding digit in AN is 6, then we make it 7. The number b that we end up with is clearly in 0, 1, so by our assumption, it is one of the ANs. But with the way we define b, it must disagree with AN on the nth digit after the decimal, so it cannot be any of the ANs, reaching our required contradiction. Since now we've shown that 0, 1 is uncountable, and 0, 1 is contained in R must also be uncountable, and we're done. If this result strikes you as unexpected, needless to say, that was the case as well a century ago. In fact, Cantor used a similar argument to show that there are an infinite amount of sizes for infinities. We call being countable Aleph null, the size of reals Aleph 1, the next size Aleph 2, and so on, which sparked many debates amongst mathematicians back then. In this section, we'll briefly discuss measure, a way to assign length to subsets of R. But since size and length are very similar concepts, it's very natural to wonder whether they're connected in some ways, which is a question we'll explore later. Very crudely speaking, the measure of a set tells us how much space it's taking up on the real line, if we were to measure it with something like a ruler. For some sets, we have a good sense of what its measure should be. For example, the interval 0, 1 takes up 1 unit of space, so it makes sense that its measure is 1. For this video, we'll define the measure of the interval AB to be b minus a. Basing off intuitions again, it makes sense that a set with only one point should have no length, or we can say it has measure 0. But to see whether this is true, we must first define what it means to have measure 0. We say that a set S has measure 0 if for any positive length, we can cover it with intervals with equal or less total length. This is like saying if you have a non-negative number m, and that m is less than any positive number, then m could only be 0. More formally, we say that S has measure 0 if for any positive epsilon, we can cover S with intervals whose total length is less than or equal to epsilon. Side note, this symbol epsilon is synonymous with small positive numbers in analysis. Under this definition, the set containing just the point P would have measure 0. This is because for any positive epsilon, the interval with length epsilon centered at P contains the point and has length epsilon. We can easily modify this to show that sets containing finite points also have measure 0. If there are n points in the set, we can take intervals of length epsilon over n around each point to cover it with intervals of total length epsilon. I teased earlier that we'll try to relate cardinality and measure, so let's look back at our previous examples and see if we can spot any patterns. Starting with the natural numbers, n is composed of scattered points, so intuitively it shouldn't have any length, and luckily for us this is true. When there was only a finite amount of points, we used intervals of the same size around each point that shrinks according to epsilon to show that its measure is 0. Here we'll take infinitely many intervals of decreasing length around the points to achieve the same effects. First, we'll need the well-known geometric sum 1/2 plus 1/4 plus 1/8 and so on equals 1. This is something crucial to our proof. To see this geometrically, let's consider a 1x1 square which has area 1. If we cut parts of the square in half repeatedly and add all the components together, we can see the results. And of course, replacing 1 with epsilon here gives a similar sum that we'll use later. Let's choose a positive epsilon. For our proof, we need to cover all numbers in n with intervals whose total length is less than or equal to epsilon. We can do this by the following. For each natural number n, we wrap the point n within an interval of length epsilon over 2 to the power of n. Then the total length of our intervals will be epsilon over 2 plus epsilon over 4 plus epsilon over 8 and so on, which is equal to epsilon using our infinite sum, showing that n satisfies the condition to be measure 0. Let us skip the integers and think about whether the rationals also has measure 0. It is countable just like the natural numbers, but trying to cover it with intervals with a small total length just feels like an impossible task. After all, the rationals are everywhere, so doesn't that mean we have to cover the whole R, giving a measure of infinity? Despite the convincing intuition, that actually isn't true. In fact, the rationals has measure 0, and so does every countable set. And it's not too hard to show this. Let A be any countable set. Then it is possible to index it by A1, A2, and so on. And now, just like what we did with the natural numbers, we can simply wrap each an in an interval of length epsilon over 2 to the power of n. Sometimes, the intervals can overlap with each other, but even in the worst case scenario, with none of the intervals overlapping, the total length will just be epsilon by our infinite sum, which completes the proof. So the impossible task of covering the rationals with intervals of small lengths is actually very much possible. Other than the countable sets, we already know that the uncountable set 0, 1 has measure 1. So after a bit of thinking, our discussion earlier could very well lead us to the following hypothesis. All countable sets have measure 0, and all uncountable sets don't have measure 0. This seems like a natural continuation of the theory that I've been building up so far, and seemed true at first glance. After all, many results in analysis were once intuitively obvious conjectures that mathematicians took for granted. So it would be tempting to assume that this too is just another theorem waiting to be proved. But as you have most likely guessed by now, this would be impossible to prove because it's false. To disprove our hypothesis, we'll need to construct what's known as the Cantor Set, which shows up in analysis every now and then to disprove over-optimistic conjectures like this one. To construct the set, we start with the closed interval 0, 1. We will call this C0. Then we cut this interval into 3 smaller ones of the same length and remove the middle one, calling this C1. For the 2 intervals in C1, divide them each into 3 equal parts and remove the middle one again for the next iteration, C2. Continuing in the same manner, for each interval in the set, we divide it into 3 equal parts and remove the middle one inductively to get each Cn. By taking the limit as n goes to infinity, or formally taking the intersection of all the Cn's, we get what is called the Cantor set. Let's try to understand this construction more by looking at what points are in the Cantor set. We can see that some points are definitely not part of C. For example, this one gets removed after a few iterations, and so do these. But if a point is once on the boundary of an interval, then it will stay as a boundary for the next iteration and so on forever. And so this point is in C. In general, these boundary points are always in C, but a common misconception is that C is entirely made out of boundary points, which is not the case. Since we want to use C to disprove our hypothesis, we need to show that C is both uncountable and a measure 0 set. Starting with being uncountable, we'll use another set that has the same size to help out with our argument, with that being the set of all infinite binary sequences, which we'll call B. We must first show that the 2 sets are indeed the same size, so we want to find a bijective map or function from C to B. Let us look back at our construction and fix a point x in C, and define the sequence it is mapped to as follows. Starting at C0, this point ends up on either the left interval or the right one in C1, so let's assign 0 or 1 as the first digit of the sequence respectively. Now for the interval that the point is on in C1, we once again see if it lands on the left or right one in the next iteration, and assign the next digit in the same way. If we continue in this manner, we'll arrive at an infinite binary sequence. This function has an inverse, since we can follow the sequence in a similar way to reach a point in C. If the next number in the sequence is 0, then move to the left interval in the next iteration, otherwise go to the right one. Recall that a map which has an inverse is bijective, so f is bijective, meaning that b and c have the same cardinality. And now most of the work is done, since we can once again use Cantor's diagonal argument to show that b is uncountable. Suppose that b is countable, then b is equal to b1, b2, and so on. Laying out the binary sequences in the same manner as before, we define a new sequence b' like this. The nth number in b' is the nth number of bn but flipped. This means that 0 goes to 1 and 1 goes to 0. Once again, b' should be one of the bn's since it is a binary sequence, but it has to be different from all bn's on at least the nth number, so we reach a contradiction, and b must be uncountable. Next up, we'll have to show that the Cantor set has measure 0, which is a surprisingly trivial task. If we look back at our construction, C is contained in each of the Cn's, and each Cn is composed of 2 to the power of n amount of intervals of length 3 to the power of negative n. So the total length of Cn is 2 over 3 to the power of n. And since 2 over 3 is less than 1, as the power gets larger and larger, the length of Cn can get as close to 0 as possible, so C has measure 0. Having now completely shattered our hypothesis, there is something else that I'd like to explore. If we go back to our discussion of cardinality, we actually see that every interval is uncountable. We could prove this easily by scaling and translating the interval 0, 1. This begs the question, is it true that any uncountable set must contain an interval? Well, the Cantor set has already given us the answer, so let's quickly show that C, despite being uncountable, contains no intervals. Recall that for any natural number n, C is contained in Cn. Let AB be any interval and denote its length epsilon. Since Cn is composed of disjoint intervals of length 3 to the power of negative n, simply find n large enough such that epsilon is bigger than 3 to the power of negative n. Then we can see that there is no way for AB to be contained in Cn, which means there's no way for it to be in C either. Therefore, the Cantor set does not contain any intervals. Hopefully by now, our theme of showing how unreliable intuition could be has made itself clear. But beyond these examples, the Cantor set holds even more surprises. In the next one, we'll use it to construct a function that sounds impossible to exist. We'll now turn our attention to analyzing the amount of times a function can cross the axis. To introduce the main definition for this section, we first need to define continuous functions. This property is seen almost everywhere, since most functions you can name are probably continuous. You may have heard a popular informal definition that goes, a function is continuous if you can draw the graph of it on a piece of paper without lifting your pen. But being continuous is not a property of the function itself, but a property of the function at a point. The function drawn in red here is really only discontinuous at this point where there's a jump, and everywhere else it behaves perfectly normally, just like the function drawn in green. An even more extreme case is the Tomei function. I'll give you some time to understand its construction, but from a rigorous standpoint, this function is continuous at all irrational points and discontinuous at all rational points. However, defining continuity formally is itself an extremely difficult topic, so we'll deal with the informal definition for the rest of the video. With this in mind, we can define whether a point is crossing the axis. A continuous function crosses the x-axis at a point P if f of p is 0, and for any small interval around P, there is a positive point and a negative point within the interval. Here, a positive point means a point that is mapped to a positive number, and a negative point is a point mapped to a negative number. To put this in terms of symbols, a point P is a cross if f of p is equal to 0, and for any positive delta, there is a positive and a negative point in the interval p minus delta to p plus delta. We can see in this example that the dotted lines lead to a positive and negative point on the left and right respectively, so the point P count as a cross here. Before we move on, let's look at a non-example. The point x equals 0 for the function f of x equals x squared. Even though f of 0 is 0, the function is positive everywhere, so there are no negative points. So this point is more like a dip rather than a cross. Another thing that I want to bring up is to try and see the definition in a different perspective. Instead of thinking about being able to shrink the interval, we can say we zoom into the point. Then it's clear why we need to be able to zoom in as much as possible. In this example, the origin looks like a cross from far away, but the cross is actually nearer, with the origin being just a dip once you zoom in far enough. With the definitions all introduced, we can finally ask the big question. What's the possible amount of times a continuous function can cross the x-axis? There is clearly a function with 0 crosses, and we have seen that f of x equals x has 1 cross. In general, we can connect some straight lines up to get any amount of finite crosses. Even the task of finding a function with countable crosses is not that tough. Recall from trigonometry that sin of n pi is equal to 0 for any integers n, and this counts as a cross. So if we take f of x as sin of pi x, then the set at which f crosses the axis is precisely the integers, which is a countable set. Despite how quick we're able to find examples for the earlier cases, the question of whether there's a function with uncountable crosses is a lot trickier. For me, my first instinct when I see this question is that there's no way it's possible. Geometric intuition leads me to think that each cross will need to take up some space for the positive and negative branches, and having an uncountable amount of these spaces will just lead the function to collapse to 0. So I was genuinely very surprised to find that constructing such a function is possible. In order to construct this function, we first need to have an idea of what the uncountable set of crosses will be. And this is where our old friend from the previous section, the Cantor Set, comes back into the picture. A crucial property that we'll need from C that is different from most other uncountable sets we know is that it is totally disconnected. We've shown earlier that C does not contain any intervals. In a way, we can interpret this as there being a little bit of space between all the points in C. This space is how we're able to make the function cross at that point, instead of being 0 near it. If we started with some other uncountable sets like 0, 1, the function would not be able to cross the axis at all the points in 0, 1, since you would just have a function that is 0 everywhere in that interval. Using this piece of intuition, our first step will be constructing a continuous function that exploits the little space between points that I mentioned. Such a function should be 0 everywhere in C and just barely non-zero everywhere else. To be precise, we'll be using the distance function from C, as shown here. For a singular point, let's say the point x equals 1, the distance of any other points from x should be obvious. 3 has a distance of 2 from 1, for 5 the distance is 4, and for negative 1 it is 2, and so on. If we plot out this distance from 1 as a function, we would get this function, the absolute value of x minus 1. Similarly, we could say that the distance of x from a point A is the absolute value of x minus a. Using this, we will define the distance of a point x to a set S as the minimum distance of x to a point in S. Here we've plotted the distance function of the natural numbers. We can see that 2.3 is 0.3 away from the nearest natural number 2, and 4.54 is 0.46 away from its nearest natural number 5. Another example that we've shown here is the distance function to the interval 0, 1. We can see that for negative x, it is closest to 0, so its distance is the absolute value of x. If x is in 0, 1, its closest point is obviously itself, so the distance is 0. And lastly, for x larger than 1, its closest point is 1, so the distance is x minus 1. We'll show a few more examples here. The one we need to focus on is the last example, the distance function to the Cantor set. It is clear from the graph that this function is continuous, and this is quite close to being our function with uncountable crosses. We have zeros at the Cantor set, and non-zero spikes everywhere else. If you recall from earlier, with x squared, x equals 0 doesn't count as a cross for the function, since the function is only positive. If we call this a dip, then the distance function already has uncountably many dips. The last step to making it have uncountably many crosses instead is to flip around some of the spikes around the x-axis. Let's, for a final time, think back at how we constructed the Cantor set. We could actually get the distance function of c in a different way. Let's consider the distance function to c0 first. Going from c0 to c1, we remove the middle interval, so a new spike is formed in the distance function of c1. Continuing in the same manner, from c1 to c2, we removed two smaller intervals here, which creates two smaller spikes in the distance function of c2. As we increase n, we can see that the old spikes from previous iterations are reserved, and new ones are added. And if we let n go to infinity, we will have reached the same distance function to the Cantor set. Now we can define a sequence of functions, fn, by altering this process slightly. f1 is still the same as the distance function of c1. For f2, we will otherwise end up with two new spikes here, but instead we'll flip them to be negative spikes. We repeat the same steps in constructing the distance function for Cn, but in even iterations, we will invert the new spikes to be negative ones in Fn. Letting n go to infinity again, we get a similar but different function, which is still continuous. And this right here is actually our solution, crossing the axis at every point in C. To show that every point on C is a cross, take any point P on the Cantor set and any positive delta. We need to show that there's a positive and negative point in the interval p minus delta to p plus delta, which we've drawn here. We now do something similar to a proof we did earlier. Starting at c0, we move down until there's an interval, part of Cn, completely inside our delta interval. This is always possible as p is in C, so it must be contained in an interval in Cn for every natural number n, and with each iteration, this interval shrinks by 1/3. So eventually it will lie completely inside our delta interval. Finally, if we think about what happens with fn plus 1 and fn plus 2 inside that interval, we'll get a positive and negative point, which completes our proof. Congrats, you've made it to the end of the video. I hope you have enjoyed this semi-introductory journey on real analysis, and that it has encouraged you to explore this beautiful field of mathematics. The maths in this video are certainly challenging, and in creating this video, I wanted to offer a new perspective to understanding these concepts. One of the main subjects of the video, the Cantor set, has so many cool properties that we couldn't find time to cover. It's known as a perfect set, and what's more crazy is that it has a dimension of around 0.63. If you can't tell, real analysis is one of my favorite topics in mathematics. I find it so fascinating, and I hope that I've successfully piqued your interest in it as well. Lastly, I want to say that we're very grateful for everyone who's taken their time to give us feedback and help us improve, and of course you, the audience, for watching this video. If you liked what you saw, please like and subscribe, and stay tuned for our future videos.